Okay, so this experiment was a synthesis of benzocaine, and it was done by myself, Alyssa Mitzderfer, and my partner was Ben Esquivel. So a little bit about the abstract. So this experiment basically involved an acid catalyzed esterification of a carboxylic acid using a primary alcohol. Benzocaine was the ester derivative that was formed. Overall, the experiment was a success as the IR spectra analysis showed that the presence of the functional groups that are in benzocaine was found in the experimental IR. And then the percent yield was a little bit low at 17.43%, and the melting point was slightly off at 87.2, but I'll get to why those values are off soon. So a little bit about benzocaine. The actual name of it is ethyl 4-aminobenzoate. And like I said before, it is an ester derivative. And you can see on the right there that figure 1 is the actual ester structure. Esters are pretty useful in common everyday uses, such as fragrances, essential oils, glycerides, lipids, DNA, plastic. Um, so in the case of benzocaine works as a topical local anesthetic, which means like you put it on the skin and it numbs the localized area by blocking nerve signals in the body through the skin. Therefore, it's used to treat pain-related issues like sunburns, sore throats, earaches, and stuff like that. And then to your right in figure 2, you can see the actual benzocaine structure with the amine group, an aromatic ring, and an ester. So a little bit about how benzocaine can be formed. One method is Fischer esterification. It forms an ester from a carboxylic acid, and a carboxylic acid is treated with an alcohol and an acid catalyst. As a side product of esterification, water is formed, and then, like I said, benzocaine can be made using this process. And in the figure below, you can see that the primary alcohol is used to convert the carboxylic acid to the ester, and the key bonds that are formed is the C to the O to the R, and then the C to the O to the H is broken. So a little bit more about esterification. A problem with it is that it's reversible. So the amount of ester that's made needs to be increased by using Le Chatelier's principle, which we could do this by using the alcohol in excess, by using it both as a solvent and a reactant. This makes sure that the reaction proceeds to the right, which means that we want more ester, or in this case, benzocaine. We can also use a dehydrating agent, and in this case, the strong acid was H2SO4, and that was used as a dehydrating agent. Other ways to remove water would be through like physical means, and that would be heating or distillation. In the case of this experiment, heating through reflux was used. So a little bit about the mechanism. So the carboxylic acid attacks a proton from the alcohol, or excuse me, just attacks a proton. So it forms this ion that then the alcohol attacks, and you form this first tetrahedral intermediate with 3 OH groups. However, then water comes in and it attacks one of the OH groups, and the electrons move around, and this is the second tetrahedral intermediate. And finally, you get your ester and a side product of your acid catalyst formed again. So, more specifically about the synthesis, by benzocaine synthesis, you could see that the p-aminobenzoic acid reacts with the primary alcohol via an acid catalyst, in this case sulfuric acid, to form benzocaine. And therefore, the overall purpose of this experiment was to use acid catalyzed esterification to synthesize benzocaine. So, not going to read this word for word, but basically, p-aminobenzoic acid and 2 milliliters of ethanol were placed into a conical vial. Then sulfuric acid was dropped dropwise through a needle into this vial, and the vial was heated under reflux for 20 minutes. Since we had a little bit of issue getting our solution to fully react and clear up, we had to add a little bit more ethanol, and then 0.1 milliliters of sulfuric acid were added. And then we actually had to heat it for 45 more minutes under reflux. We finally got the solution to clear, so we poured it into a beaker with 5 milliliters of water. Sodium carbonate was added until the pH was around 8. We then had our crude benzoate, which we collected using vacuum filtration and rinsed it with cold water. We air dried and weighed that, and then purified the benzocaine with more water and methanol, and then air dried that and took the weights, and then eventually we found melting point, percent yield, and the IR spectra for the pure benzocaine. So a little bit of our results. The grams of crude product we had was 0.054, and then the grams of pure product was 0.042. Little bit of mass loss there for several reasons, which I'll get to later. The actual melting point of benzocaine is around 88.9. Ours was pretty close to that at 87.2. Here you see the actual IR spectra of benzocaine. Right around 3400 is where you see that amine group that's present in the molecule benzocaine. Just moving a little bit forward, so the peak at 1500 is the aromatic ring, which you can also see in this actual IR spectra. And then here's the experimental IR spectra, which again, you see the 3400 peak being kind of sharp, indicating that there's an amine group there and really not the presence of a whole lot of water. If the water had been there, the peak would have been a little bit more broad, and that would have thrown off the percent yield and melting point as a result. In addition, 800, around 800 inverse centimeters, you see another peak that indicates that same amine group. And then finally, the ester is indicated at approximately 1200 inverse centimeters. So I included a little bit of a diagram that circled which functional group I was talking about to make it easier. So A was the amine, B was the aromatic ring, and C was the ester. So my sample calculations show how I calculated percent yield. I found that the p-amino benzoic acid was the limiting reagent, and I did that by converting the grams to moles and then the moles to grams of product, and so forth with the primary alcohol. I used my actual yield divided by, or my theoretical yield, my obtained yield, over the theoretical yield times 100, and I got 17.43%, which is a little lower than we would have expected. But the IR spectra analysis tells me that this experiment was a success because I did get benzocaine essentially due to the peaks all matching up in the actual and the experimental IR spectrum. So like I mentioned before, the melting point was 87.2, which is pretty close to the actual at 88.9. So the reason that the melting point was slightly off and the yield was a little low is that we could have had some mass loss, and I know we had some mass loss when we were transferring the product from the filter paper to the watch glass for weighing. I find that in a lot of our synthesis reactions, I guess, I'm losing a lot of my products stuck to the filter paper, and there's really nothing I can do about that besides get it off to the best of my ability. But I do know that some mass was lost, which as a result would lower my percent yield. And then another thing that I found that we may not have done completely was that we didn't either stir enough. We could have probably scratched the glass to induce crystallization, or I didn't quite add enough sodium bicarbonate, so I didn't let all the solid form in order to get all of that pure benzocaine, or crude benzocaine, excuse me. So I think that if I would have done the experiment slightly differently, I probably would have given the reaction more time, especially under reflux, because although the solution looked clear, there was probably a little bit of solid left in the bottom. So I don't think we got as much pure benzocaine as we could have. So yeah, if I were to go back and do something different, I'd definitely take my time on a couple more steps, like the stirring, adding sodium bicarbonate, and the heating. And that's it.